Hi, I'm going to tell you about our paper, Stable Sample Compression Schemes, New Applications and an Optimal SVM Margin Bound. This is joint work with Aryeh Kontorovich. The subject is data-dependent packed generalization bounds for classification. Let's start with some basic notation. It's all pretty standard in statistical learning theory. There's an instance space X, there's a label space Y, and here Y is just going to be -1 and 1. There's some unknown distribution P on XY pairs, and we'll define the error rate of any classifier as the probability it makes a mistake on a random XY from that distribution. Generally, we'll define a learning algorithm as taking a data set of some size n as input and outputting a classifier. And we think of that data set as being sampled IID according to the distribution P. Also, for any classifier, we'll define the empirical error rate as the fraction of data it makes mistakes on. We'll be interested in data-dependent packed generalization guarantees, and by that I just mean bounds on the error rate holding with high probability 1 minus delta, where the bound might be a function of the data itself. Now, the main idea here is that we'll use a recently introduced technique known as stable compression schemes to prove several new data-dependent generalization bounds. And as the main example of this, we'll present a new margin bound for support vector machines, which is provably optimal. This actually resolves a long-standing open question. We'll also apply the technique to show that the Perceptron algorithm also achieves the optimal margin bound. Finally, we'll also derive a new agnostic pack bound for stable compression schemes, and we'll give an application of that to sharpen a bound for compressed nearest neighbor classifiers. Okay, let's begin with some background on SVMs. The support vector machine is a classic learning method for linear separators proposed by Vapnik and Chervenenkis. And in the case of separable data, it simply chooses the maximum L2 margin linear separator. One important approach to understanding generalization of SVM is margin bounds. Specifically, if we let R denote the largest norm of the data points, and we let gamma denote the margin of separation for the maximum margin separator, then a remarkable fact is that you can bound the error rate of the SVM by a bound that just depends on R and gamma, but is independent of the dimension of the space. The bound here was proven back in 1998, and it's what you'll find in most textbooks. It's also not hard to prove a lower bound in terms of R and gamma, meaning that no algorithm can guarantee an error bound in terms of R and gamma that's better than this. And looking at these two bounds, what you'll notice is there's a gap in the log factors. And this gap has since been reduced a bit, but there's still a log factor in the upper bound that's not in the lower bound. And determining whether SVM can guarantee a margin bound that matches this lower bound has been a long-standing open question in the field. In this work, we actually prove that indeed SVM does achieve an upper bound matching the lower bound and therefore has the optimal margin bound. So this resolves that whole question. Okay, so our proof of this is based on two key facts. First, what we know is if you express the max margin optimization in its dual form, the SVM weight vector becomes a linear combination of training examples, and only some of the points have non-zero weight, and these are called the support vectors. Now, the first key element of the proof is that it turns out there's always a solution with at most R squared over gamma squared support vectors. The proof of this fact starts with an observation from Vapnik and Chervenenkis that there are at most R squared over gamma squared essential support vectors, meaning support vectors where if you remove them from the data, it actually changes the SVM classifier. We'll use this in our proof by imagining inductively pruning away non-essential vectors one at a time until we're left with a data set where every point is essential. So there must be at most R squared over gamma squared points left. And since each step only pruned a non-essential vector, the SVM on this subset is the same as for the full set. So that's the first key element. The conclusion is that SVM can be expressed as what's called a compression scheme with size at most R squared over gamma squared. But then our second key element of the proof is that the fact that it's not just any compression scheme, it actually has a special property. So it has the property that if you remove any portion of the data set, as long as what you're left with still contains a complete set of support vectors for some solution of the original problem, then the SVM classifier for that subset will be the same as for the full data set. And this is what's called a stable compression scheme. Okay, so right now, to explain why these two key facts together resolve the margin bound question, let's talk about some recent developments in generalization bounds for stable compression schemes. Now, generally, a compression scheme is a type of learning algorithm. It's described by two functions, a compression function kappa and a reconstruction function rho. And given a data set, kappa selects a possibly ordered subset. And if you feed that into the reconstruction function, it returns a classifier. And we say that a compression scheme is stable if, for any subset of the data, as long as it contains all of the compression points, applying the compression scheme to that subset still returns the same classifier as applying it to the full data set. So this is just like the property I mentioned for SVM. Now, for a general compression scheme, there's a classic generalization bound from Littlestone and Wormuth. It says that if the compression set size is always bounded by some number k, then with probability at least 1 minus delta, if the classifier is correct on the data, then its error is bounded by k over n log n plus 1 over n log 1 over delta. However, this isn't good enough for us because of this log factor. And in fact, it's known that for general compression schemes, this log factor can't always be removed. However, for stable compression schemes, it can be removed. This is actually a recent result from last year's COLT from a paper I wrote with Bousquet, Morin, and Zhivatovsky. It says that if the compression size is bounded by some k, then with probability 1 minus delta, if the classifier is correct on the data, then its error is bounded by k over n plus 1 over n log 1 over delta. Okay, great. So we're going to use this. But for our purpose here, we actually want to make this slightly stronger before we can use it. Basically, we let the compression size in the bound just be whatever the size of the compression set happens to be for that data set. And this way, we're expressing it as a data-dependent bound. This isn't too hard to get. You just basically do a union bound over the different possible values of the compression size. And this is the main tool we will use to derive most of the results in this paper. Okay, in particular, we can now return to discussing the margin bounds and use this result to finish off the proof of the SVM margin bound. Okay, so putting these pieces together, SVM is a stable compression scheme with compression size at most r squared over gamma squared. So we can just plug that size into the bound for stable compression schemes, and we get that in the separable case, with probability at least 1 minus delta, the error bound is r squared over gamma squared, 1 over n plus 1 over n log 1 over delta. And if you'll recall, that's the exact same form as the lower bound. So we can conclude that SVM indeed achieves the optimal margin bound. Good. What's also interesting is we can use this same technique to get an optimal margin bound for Perceptron as well. So the Perceptron is a classic learning algorithm for linear separators. It was proposed by Rosenblatt. And basically what it does is it goes through the data, and whenever it makes a mistake, it adds that point times its label to the weight vector. And so let's imagine running this algorithm through the data set, updating on each mistake, and in this case, just keep cycling through the data until we make a complete pass through the entire data set without making a mistake. And then just output that final classifier as our H hat classifier. So this is a very simple way to use the Perceptron algorithm to learn a linear separator. Okay, now in terms of margin, there's a classic result from Novikov that says the Perceptron will update at most r squared plus 1 over gamma squared times. And since the final classifier is completely determined by these updates, this algorithm can be viewed as a compression scheme of at most this size. And then we can also observe that the compression scheme is in fact stable, since the algorithm basically ignores all the data points it doesn't make mistakes on. So if we remove any subset of the points that the algorithm never made a mistake on and rerun the algorithm, we'd still get the same final classifier. Okay, so then just plugging that into the result for stable compression schemes, we immediately get that in the separable case, the perceptron algorithm also achieves the optimal margin bound. Okay, great. And yeah, this stable compression bound seems to be very useful, right? And in the paper, we also give a few other applications. We bound the probability in the region of disagreement of a version space, and this leads to refined data-dependent bounds for general ERM learners and for active learning. I'll just refer you to the paper for those details. But for now, let's move on to discuss one final topic, which is agnostic pack bounds for stable compression schemes. Okay, so yeah, the theorems we've been using, this main theorem was expressed, or the main tool that we've been using is expressed only for the separable case. And it's natural to ask, what about when the returned classifier has non-zero training error? Now there is a classic generalization bound for compression schemes, which looks like this. Basically, with probability 1 minus delta, the error rate and the empirical error rate differ by at most this bound, which is roughly the square root of the bound from the separable case. You see the bound has this log factor in it. And actually, in a paper at Alt 2019, we showed that for general compression schemes, this log sometimes can't be removed. But what we show in this work is that for stable compression schemes, the log can always be removed. So just like in the separable case, the log factor goes away for stable compression schemes. I can state the proof here in a decent amount of detail. It's a little more involved than the separable case, but I can still present it in one slide. I'll just present here the version where compression size is bounded by some k. To get to the data-dependent compression size, you would just do a union bound over compression sizes. So also for simplicity, let's say n is a multiple of 2k. Okay, now for the proof, let's imagine, first just imagine we split the data randomly into 2k equal size sets. And then by Hofting's inequality and a union bound, we have that for any k of these sets, applying the compression scheme to the union of those k sets, the error rate and the empirical error rate on the union of the other k sets differ by at most this bound, the square root of 1 over n log 2k choose k 4 over delta, right? That's because those sets are independent. Okay, so, and then just we can simplify this a bit. 2k choose k is bounded by 4 to the k. So that simplifies into this bound on the right-hand side. Great. Then let's note that the compression points are contained in some k sets. And then stability implies that applying the compression scheme to the union of those k sets returns the same classifier h hat as applying it to the full data set. So combining these two facts gives a bound as stated here. Now, the only reason we're not done yet is that the empirical error rate here is only being evaluated on half of the data set. Now, to get a bound in terms of the empirical error on the full data set, let's note that since these B sets are randomly constructed, for any choice of K sets, the data not contained in those sets are a random sample from the full set. So we can use Hofting's inequality for sampling without replacement together with the union bound, and we get that for any choice of the K sets, the empirical error rate of H hat on the data not contained in those sets differs from the empirical error rate on the full data set by at most this square root bound here. We just apply this to the K sets containing the compression points and put this together with the first part of the proof, and that completes the proof. All right. And we can also prove a kind of Bernstein form of the bound where the empirical error rate also appears inside the square root. This way the bound interpolates between the separable bound and the square root bound. You can see the paper for the details of that. As an application of the agnostic bound, we give a refined analysis of a compression-based nearest neighbor classifier. Specifically, in a separate work by Kontorovich, Sabato, Weiss, and myself, we propose an algorithm we call OptiNet. it has a really neat property that it is universally consistent in every metric space where there exist universally consistent learning algorithms. The way the algorithm works, for each epsilon, the algorithm constructs an epsilon net of the training data, and it then takes the predicted label within each cell of the Voronoi partition as the majority vote label among the data in the cell. And that classifier can be interpreted as a nearest neighbor predictor based on the data points in the epsilon net, but replacing their original labels with these majority vote labels. So then we have to choose a resolution epsilon, and it does this by a kind of structural risk minimization approach, optimizing a bound on the error. And since the nearest neighbor classifier is a compression scheme, essentially compressing to the epsilon net points, then the bound that we're optimizing here is a bound based on the compression size, the epsilon net size. Okay, but now we can notice that that actually, if the epsilon net is constructed in the sort of natural greedy way, then the compression scheme is also stable. So in fact, we can replace the bound in that optimization step with our new bound for stable compression schemes. And then the result is an improved error bound for the overall OptiNet learning algorithm. Okay, so to summarize, stable compression schemes are a useful perspective for proving sharp data-dependent generalization bounds. SVM and Perceptron both achieve the optimal pack margin bound, and we have established a new bound for stable compression schemes in the agnostic case, which, just like the separable case, removed a log factor from compared to the bound for general compression schemes. Thanks.